solving the Thevenin Equivalent Circuit, and we're going to be looking for maximum power on the load resistor. Thevenin circuit module introduces a powerful technique for simplifying analyzing electrical circuits by representing complex circuits as equivalency voltages and resistances. This method provides engineers a practical approach to predict, evaluate circuit behavior under various load and conditions. Theoretical calculations, simulations using multisim and hands-on experimentation with Analog Discovery 3 offers an in-depth understanding of the principles and application of the Thevenin Equivalent Circuit. This module combines theory and practice to ensure comprehensive learning experience. The objectives of this module are to equip learners with both analytical and practical skills in circuit analysis. The processes for constructing Thevenin equivalent circuits for resistive networks will be explored, starting with computer simulation and progressing into hardware setups. Expertise in measuring Thevenin equivalent voltages and resistances will also be developed using industry standard tools like Multisim and Analog Discovery 3. These objectives align with real-world applications, enabling confident tackling of engineering problems related to circuit simplification and load analysis. So first off, we're going to look at the circuit we've built up. We have V1 right here, and then what we have here is a complex circuit. But as soon as you start analyzing this, especially when we're using the Thevenin equivalent, this right here kind of becomes removed, and you can start looking at this circuit as more like a bridge circuit, where these would be your loadouts here and here. So the first thing we're going to do is replace the voltage supply with a short. So we'll go and delete him, and then from here, go up here and just short this out. On. Control C that. I want that to go to the ground. Whatever. There we go. Let's see if we can pull this back over this way. There we go. There. Now we have this source here, and I'm also going to get rid of this right here and turn it strictly into a bridge circuit. Now into this bridge circuit, I'm going to go ahead and put my multimeter, and we're going to put probe 1 right to here, one side of the bridge circuit, and the other probe over here to the other side of the circuit. Now this is going to measure my Thevenin voltage. Now Thevenin voltage, Thevenin resistance for this circumstance would be the resistive equivalence of R1 and R2 added to the resistive equivalence of R3 and R4, which the math of that looks something like this right here. Now, when we do the equation, we're firing our resistive Thevenin equivalent portion. We would take our resistive equivalence of R1 and R2 plus the resistive equivalence of R3 and R4, and then we would add them together. So resistive equivalent 1's right here, that's the first portion right here, and the resistive equivalent right here, the second portion right here, and then they just get added together, and we end up with, because they're going into the second, coming like in series together into here, because these two are in series. Now we end up with, we go over here to our multimeter, and we have, look at that, 1.259 kiloohms. Next we're going to be finding our Thevenin voltage. Now since we have calculated our Thevenin resistance, we're going to reintroduce the voltage source. So we'll go over here to power sources. We'll go to DC power. Okay, now it's important that when I reintroduce this, that I readjust this back down to 5 volts, because we are currently on 12, we want to be on 5 volts DC. Now, we've removed the resistor over here. We want mega ohms here. Now, there's two ways we can do this. We could first take our multimeter, bring him back in here, and reconnect him to either side. And this would read us the difference in voltage potential between the two, which should give us 3.479 volts. Now, if we go over here and look at our actual calculations, we would take V1, which is 5 volts, multiply it by R3 over R3 plus R4, and this would get us VR34. This is this portion of the current, or the bridge circuit. And over here we would do the same thing. And by the way, a bridge circuit is literally two voltage dividers just kind of squished together, and then you're reading off the middle of them. And what it does, you can do a lot of things, but in this case, what it does is will give us a voltage between the two at a certain point, and what it is the voltage differences between the two. So we do the same thing with R1 and R2, which is over here, and we will go ahead and do this R2, because it's the bottom portion, because the current's going this way, so we're reading off the voltage here would be the same as parallel over here, so they would have the same voltage drops. Once we get those two voltages, we would end up going, and if we can even look at this real quick, if I place a probe, voltage probe, across here, and here, we take these two voltages and subtract them from, we end up with 3.479. So that's literally what's going on here. I'll delete these back off, and that would give us our Thevenin voltage, which is going to be 4.78, 4.79 over here. But I mean, they're rounding differently probably than I'm doing over in my calculations over on MATLAB, because I have 3.48, so if I go to a third decimal place on my Thevenin voltage, see what we get. So, yep, 3.479. I probably just wrote it wrong on my thing, but I'll correct that right now. Perfect. That gives us our Thevenin voltage. Next, we're going to find our Norton equivalent current, starting by treating the load resistor as a short. In this case, we go ahead and put 0.1 ohm resistor there. So it's very small. It's 100 milliohms. But considering the rest of this is well over that, it's going to have very little resistance between the two. This calculation is very straightforward, though. Since we've already found the Thevenin voltage and the Thevenin resistance, current is equal to voltage over resistance, and you can literally divide the Thevenin voltage by the Thevenin resistance, and you end up with your Norton current. So let's see what we get over here. We got 2.76 milliamps, the exact same thing as we got over here. And that gives you your Norton current. The final thing we're going to look at in this circuit on multiism is going to be what our maximum power transfer is across the load resistor. Now, according to our textbooks, maximum power obtained is when RL is equal to R Thevenin, right here. So we can take that, and this is in your textbook, power is equal to voltage times current, and we can then take that further to find our load current, and our load voltage by going into this equation right here, also in your textbook. I replaced source, this would be RS in your textbook, with Thevenin voltages, because that's what we already have, and that's what Thevenin voltage is your source input for those. We then go through the equation, and I run all my calculations through MATLAB, and we have that equation right here. And when you run it through, we end up having a maximum power of 2.4 milliwatts. And that's, let's see what we get when we go through and simulate that through the parameter sweep simulation. So we'll go up here, go to analysis and simulation, go down to parameter sweep. We're going to be doing our resistor R5, 100 ohms. We want to start it at 100 and we want to end it at 10 k ohms. So you go to K, just go hit that over there. And we want to do 100 increments. Oh, sorry, 100 points. And then linear resistance. I believe this is right. So let's go ahead and give this a run and see what we get. Nope, I forgot to output. We're looking for the power on R5. I'm going to add that in. Now let's run it. We get this nice sweep. I'm going to start by increasing the trace width to about 5, so it's a little bit easier to see what we're doing here. I'm going to go ahead and make this big as well. Now, I'm going to take these two and get them as close to either side of the maximum of this. I think the maximum probably right about there. So we say our maximum, our RTH, our Thevenin was 1259. So I can get X1 closer to 1259. 1229, okay. On the other side, X is at 13. We bring that a little bit closer. And it's now down to 12876. We'll say 1261, that's pretty close. And you can see how close these are together. Now if we want to, we could actually zoom in on this portion. Get a little bit further away. .59. And if you look at the wattage, which the wattage is this one here on the Y, because you're going Y alpha power. So 2.4, 2.4. And notice this 2.4 is a little bit bigger than this one right here, and as we get closer to it, with this one, it gets closer to where we're at. And we look at our calculations, and we got 2.4 milliwatts, which is exactly what we're showing out here on our parameter sweep. Okay, now let's look at our breadboard setup over here. Now I have it currently set up with to read for Thevenin resistance, and if we remember what our Thevenin resistance was, it was back up over here so we can just see it on my screen. Thevenin resistance was about 1259.06 ohms, and we're reading 1243. Now keep in mind we have slightly different resistors, and we'll go through those numbers of the alternated numbers, which come up to be, so we've got R1 at 6660 with a 2% error, R2 with 989 with a 1.1% error, R3 at 2142 with a 2.64% error, then R4 at 4.61 for a 1.9% error. Now if we look in here, I've got this would be R1, R2, R3, R4 right here in these resistors right here. Move this down a little bit so you can see a little better. Notice I have currently I have the power, instead of it going to power, it's just shorted across there. So we end up with a circuit like we had earlier of our Thevenin where this was removed and we're reading across this. Now let's go ahead and plug those numbers into MATLAB, have our actual numbers put in, and we have resistor 1 being 6.66 kiloohms, R2 being 0.989 kiloohms, R3 being 2142 kiloohms, and then the final one being 0.461 kiloohms. Okay, and let's see what we get for our new, oh, I put another point in there I didn't need. We end up with a Thevenin resistance of 1240.48, which is 3 ohms off. So there could be a difference just within stuff between them, giving us a little bit higher resistance, which is completely normal. It's plus or minus within a easily 1%. Actually, I think it's 0.1% at that point, because we're looking at 3 ohms over thousands, 1,200. With that done, we can next work on finding our Thevenin voltage. And to do that, we will go ahead and connect into we'll remove this from here. And instead of going across, we're going to have it go to ground on our analog. Plug it in for our waveform here shortly. Next, we're going to go ahead and take the power portion and plug it into where power goes instead of being into ground. We will then set our flute to volts DC, and then we'll go into our waveform simulator, and we'll go to supplies. I want to change this to 5 because we're only using this one, so I'm only worried about that one. We'll go and turn this one off, and we'll master enable on. And if we remember, we're currently reading currently reading on our multimeter 3.452 volts DC. Now if we go over to our MATLAB code, it says we should have 3.468 volts DC. Once again, we have a bit of a difference in the amount of voltages we need, but it's a difference of like 0.1, see, 826, 0.016 actually, so well within our allowed deviance. Finishing our circuit, we're going to take potentiometer C502 and a 100 ohm resistor, which is right here. We're going to hook up the A portion of our bridge circuit right here, and then I'm putting the first channel right here off of the first plug pin to the potentiometer. Next, we're going to hook up the first channel for our second channel's first lead, the first pin to the 100 ohm resistor, and the second pin of the potentiometer here, and then we're hooking the last pin to our channel 2, the last pin to the resistor here, the last pin of channel 1 here, and then the B portion of the circuit there. Now in the overall bridge circuit, as we see here, we have this portion right here feeding back over to there, and this portion right here feeding back over to here. And the reason we're doing it this way, I know this looks like it's not that, but that's a green one that's going in a separate place. We're talking about this blue one, right? Sorry, thing to point with. We're talking about this black one right here. This is getting fed back over to the circuit back there, and this blue one is being fed back over that circuit. The reason being they're being fed over here, it's just, for me, in my opinion, it's just easier to move this whole portion over here out of the way, because there isn't a whole lot of room down in this area to do it. So it's the same thing. I just literally, if we go over here and look at Multisim, as you can see, it's like just moving R5 from here up to here with the jumpers, just getting it out of my way, because there isn't a whole lot of room in between here. Now, once that is set up as such on the board, and we've got these all hooked up, and I got my power coming in right there, across the circuit right there, little jumper right here across the two. But once we've got this hooked up, we can go over here to our waveforms, and I have my C1 maximum set to maximum over here, my C2 set to maximum, and my M1 set to maximum. Now, on the circuit, as you can see, I left it so this portion is exposed, so that when I go and adjust it, it's not going to be too difficult for the adjustments itself. I'm going to turn it this way, just because that actually faces me. Now over here in time, I've set it to 2-second divisions. Channel 1, I have 2-volt divisions. Channel 2, now it's important to go into channel 2, and because we have a 100 ohm resistor, we set this to 0.01 times, bringing it down, its size down. I have it set to blue. And I'm going to go to 1 milliamp divisions just because it'll make it easier to see. And then over here in our final math 1, it's going to combine C1 and C2 through multiplication to tell us how many milliwatts we're getting. Go like that. Should make it a little clearer to see. Alright, then we'll go ahead and we have our supply on. We'll go to scope and start the scan. Now currently we are sitting at a maximum of 0.7. So we'll go ahead and increase the, and as you can see, as I'm increasing it, we have our voltage going up and our current going down, and our M1 maximum, which is in purple, going up. We're going to try to get it to where it just stops going up. 2.2, we're getting close. We're at the 2.35, 2.43, 2.45, 6, 7, I think we started decreasing because it stopped saying anything maximum, so I'm going to wait a second for this to go through a full cycle, because it's showing only my maximum, so until it has a lower maximum, it won't go down. Yeah, it's gone down by 2.4 about 5. So we're going to go a little bit slower. So we got about a 2.46 maximum. And we're looking at our equation from earlier. We should have had a maximum about 2.403. So we're well within the small difference. We can even put it in here. Is and we're talking. I know it says ohms, but bear with me. So we have 2.403, and then we have 2.462. So plus or minus is in case minus 2.33%, well under 10%. A good, nice current, well within our margin for error for our current. And that's pretty much this lab.